So this video is going to be on the one-dimensional wave equation, modeling an oscillating string. What you see right here is the solution to the wave equation, and as you can see, it looks very much like a string that's been plucked and allowed to vibrate back and forth very rapidly. So I'm going to show you how you can arrive at this solution using separation of variables. Again, I'm not going to go through all the details of separation of variables because basically in order to solve for our coefficients we actually have to do a bunch of integration by parts, which is sort of lengthy, and I don't want this video to be too long, so I'm not going to get into too much detail about separation of variables, but if you want to know more about it or see its application to PDEs, then you can watch one of my earlier PDE videos. Okay, so here's a still image of the graph that you just seen. So basically what we have here is, right here, this is the one-dimensional wave equation. It's a PDE, linear. But basically the function that we're looking for is a function of x and t, and it represents the vertical displacement of the string at different times. So here are our boundary conditions. You can see that when x is 0 and when x is pi, which is the length of the string, there's no vertical displacement, so it's fixed at each end. It's not allowed to oscillate back and forth. So you can think of it like a guitar string that's fixed at either end of the guitar. And our initial condition is this here: when t equals 0, the string takes the shape of this function here, and that's actually what you're seeing here. This is the function at t equals 0. So it's just basically an upside down parabola that has its roots at 0 and pi. Its maximum at pi over 2, and its maximum height at pi squared over 4. Okay, so just really quickly, the method of separation of variables says that if you assume that your solution is the product of one function that's just a function of x and another function that's just a function of t, and you plug this into your differential equation, take the second derivatives, you find the separation constant, you can reduce this partial differential equation into two ordinary differential equations that you have to solve for. You find the eigenvalue and eigenfunction, and what you end up it's quite lengthy to do this, but what you end up finding out is that your function has this form. So this is just the standard form of the solution to the wave equation with fixed ends. Okay, so the general solution has n times pi times a times t over L. But in our example, the length of the string is pi, so when I plug in L equals pi here, the two pi's cancel, and we end up with this, where this right here, where that's a. And similarly over here, it's pi n x over L, and when you plug in pi for our length, the two pi's cancel. So this is a solution for this example. Okay, so when we use our initial conditions at t equals 0, so when we plug t equals 0 into here, you can see that this is what you end up with. Okay, so this is just a Fourier series for sine, so we know how to, we've done this a couple times already. So this tells us that those coefficients are 2 over L, or in this case L is pi. You integrate over the length of the string, which is pi again, and then it's your function times this term here, dx. So this is what's going to require integration by parts one time for this term here and twice for this guy here. It's a bit tedious. Hopefully it doesn't take me too long to do this, and hopefully I don't make any mistakes. So I'm just going to go through it quickly because this isn't a video to teach you how to do integration by parts. Okay, so I just break up that integral into this. So I perform integration by parts once on this first integral. To get this here. So just really quickly, when I hold that x constant and I integrate sine, I end up with this. I evaluate it at the two ends. So then for the second part of the integration by parts, I take the derivative of x and then I integrate this cosine here, when the result of integrating this part here. So then for this part here, I had to do integration by parts once, and you can see that I'm going to have to do integration by parts. And so, but this integral simplifies a little bit. You know that cosine looks something like this. Sorry about that. That's a terrible picture, but you can see that when I integrate from 0 to pi, this is actually 0, so that helps things out a little bit. Okay, so when I plug in these values here, and then integrate this by parts again, I end up with something that looks like this. This term here came from doing integration by parts on here, where I had to integrate cos from 0 to pi again. So I don't even need to plug anything into there. We know that that's going to equal 0. These two terms cancel. So basically I'm just left with this last integral. So when I compute that last integral, it looks like this. I do want to point out that that's supposed to be an x there. So when we evaluate this at either end, we end up with something, and we end up with this here. Okay, so we're not interested in when these constants equal 0. So we want to know, when does this not equal 0? Well, it doesn't equal 0 when cosine of n pi equals minus 1. So when does cosine of a multiple of pi equal minus 1? Well, when n is odd. So when n is odd, that equals 1. That will equal minus 1, so we have 1 minus a minus 1, so that's 2. So our constants look like this. Okay, so that means that our function that describes the vertical displacement of points along the string looks like this. Okay, so here's our solution. Now let's go into MATLAB and have a look at the code that I wrote to generate that animation of the string vibrating. Okay, so here we are in MATLAB. Let me just clear the screen. Let me open up the program that I wrote. Okay, so let me describe it a little bit. This is the length of the string. This is our array that's of the same length as each of the points along the string. So for the way that the program works is it calculates y at different points in time for each x value all along the string, and then it plots y versus x down here. Okay, so the way that it does that is I have these nested for loops. So basically it starts at your initial time, and it goes inside to these nested for loops. Okay, so it starts at one x value, and then it runs through and calculates about 50 terms of our series solution. at one time, and then at every point along the string. Okay, and then it comes out of these for loops, and it plots that first curve. Then it goes through again, goes up to the next time, and it does the same thing. It calculates the displacement for every point along the string, and then plots the resulting function again. Goes through again, time ticks ahead one more, in this case 0.05, then it goes through again and calculates the displacement of every point along the string using 50 terms of our solution. And then it plots it again, and it just keeps doing that, all at different times. At each time, it plots the displacement of every single point, and then plots that curve. So, when I run this, it looks something like this. Okay, so this time I'm not going to clear the screen after I plot each curve, but just to show you that it's actually plotting every curve at each instant in time, let me shut off this clear screen command here, clear figure command here, and show you what that looks like. Okay, so you can see that it's actually plotting each curve at each moment in time. Kind of cool. Okay, so let me put the clear screen again. And now let me slow this down and show it to you in slow motion. So here's the string vibrating in slow motion. You can see that when it goes all the way to the top, that curve that you see there is our initial curve of what is it, y equals x times pi minus x. That's the shape of that upside down parabola at the very top, right here, and at the very bottom, right here. Okay, kind of neat. So thank you very much for watching.